Recording in progress.
All right. Welcome everyone to the second day of the AAL, and we are going to start the day with our next invited speaker, Professor Dirk Pattinson from Australian National University, and Dirk is going to be talking about semantics and proof theory of non-monotonic modal logic. So please, Dirk.
Yeah, thanks very much for the introduction and the invitation, of course. I'm going to try very hard to kind of live up to the bar that Sasha put out yesterday. There's not going to be a lot of continuous mathematics, but still. So I want to talk about modal logic, specifically non-monotonic modal logic. And I want to conceive of modal logic as being something that's fairly broadly. So let's say that a mode is just a word that qualifies in what sense a certain proposition is true. So Sam is, of course, Sam Kerr, the captain of the Australian women's football team. And she is normally a good player, which means that she isn't hurt. And James, and I'll leave it to your imagination, which James I'm referring to, is possibly a spy. And there are things that are known but not true, so it makes sense to say that it's known that Sydney is the capital of Australia, despite the fact that it's not true. And there are lots and lots of examples. And these things can also be binary or even ternary, if you like. So the quote below is the first sentence from a book by David Lewis, who was an American philosopher. She spent a lot of time in Australia. And the title of the book, as you might guess from the quote, is called Counterfactuals. And these are, a counterfactual is a binary modality, that's at least the argument that he makes very believably, that you instantiate with two statements. The first one is kangaroos have strong tails, and the second one is they topple over. So modes can be binary, whatever. And of course, there are lots of different ones. So, and that depends on what we want to talk about. And also these things can be combined, and we can add modalities to a large number of different propositional based logics, positive, intuitionistic, classical, vague, whatever. So it's a wide playing field. And here's our research program. So what you can do when you want to study modal logic is you take one system and one base logic, etc., at a time. So this is, on the left, you see the sweatshop from the US in the 1890s, I believe. So you think of this as all your grad students, and they're all slaving away, and they're trying to prove, I don't know, completeness or decidability of one particular logical system. And then if they've done enough, they will earn their PhD. So what we want to do is something different. We want to look at principles that are applicable to a whole class or family of modal logics. And we want to liberate all these people that work in sweatshops by using the weapons of maths construction to get results that apply for an entire class of modal logics. And while writing these slides, I made a discovery. And the discovery is that a logician's liberation league actually exists. And we might hear about this a bit more from one of the speakers later in this conference. Let's wait and see. Okay, so let's get a bit more technical. So for the purpose of this talk, I'm just taking classical propositional logic as the base. You can take your favorite way of describing. Here I'm using propositions, negations, conjunctions. and I add generic modal operators that I like to write as hearts because I think there should be more love in this world. And they can be n-ry. And this also includes nullary operators, which are not very interesting. And we can have a unary box. So if you know cryptic semantics, then this is sort of necessarily, if you like, epistemic. This could be the qualifier. It is known that binary conditionals could be counterfactuals. It could be binary conditionals, A under the condition B. And here's a third example. So this is from coalition logic. So for every set of agents, we have a modal operator, and the modality says that the coalition can bring about a certain outcome. Whoops. Okay, so why do we want these modes? And this is the point where I can't resist to have a bit of fun with material implication. And so this is all about binary modalities, and I just love the examples, so I wanted to share them with you. So why is propositional logic not sufficient? So we have transitivity. If Bob quits teaching, he won't be able to afford his house. If Bob wins the lottery, he will quit teaching. And therefore, by transitivity, if Bob wins the lottery, he will not be able to afford his house. Which means that sort of an if-then conditional is certainly not material implication, right? Because that's clearly nonsensical. If Magellan, so this is about counterfactuals, if Magellan would not have died in 1521, he would still not be alive today. And if you take the contraposition and again package it up as a counterfactual, if Magellan were alive today, he would have died in 1521. So we really need modalities to make sense of modalities of that type. So specifically, we want something that is not truth functional. So if Charlie were in Sydney, they would be in Australia. If Charlie is, let's say, if Charlie is here, then this binary modality, or the two ingredients of the binary modality, Charlie is in Sydney, Charlie is in Australia, are both false. No, let's say Charlie would be in the UK. Anyway, just make them both false. And then also Charlie is not in London and Charlie is not in France. So that means here all arguments of the counterfactual are false. But still the first is true and the second is false. So we can't have something that is truth functional. So that means we need a different kind of semantics. And I'm gonna give you, so I feel that I'm missing out on slides. Yeah, here we are. I'm gonna give you algebraic semantics, right? And that is indeed very easy because we just take a Boolean algebra with not operators, but operations. And in order to not misspeak, I'm not calling them either. I'm calling them functions. So for every n-ary modal operator, we have an n-ary function on the carrier of our Boolean algebra. And of course, it's not required to satisfy anything. This can be highly non-monotonic, etc., etc. And then we can interpret formulae. And that's wonderful. And that means that whatever operator you're giving me, we have a semantics, which is not truth functional. That's easy to see. So whatever operators you give me, it's going to work. And we can impose axioms and equations. We can lean on universal algebra. And we get completeness for free, for example. So that's all wonderful. But specifically, if we wear a philosopher's hat, this is not what we want at all, right? Because it's just syntax in disguise, and completeness is by construction of a Lindenbaum-Tarski algebra, which kind of doesn't give any principle insight other than it's possible, yes, we can do it. And moreover, it doesn't give us anything, any help to judge whether the axioms that we've imposed to model, I don't know, for example, counterfactuals are the right ones, right in quotes. So there's no yardstick that tells us, that allows us to kind of validate the axioms. So it doesn't give us anything that allows us to say, yes, these axioms are, and I'm using a mode, probably correct. So algebraic semantics, yes, we can do it, but it's not very useful. So this is why we like to look at frames, and I'm giving you an intentionally imprecise definition. And if you hold me at knife point, I can make this ridiculously precise. Let's just stick with this for the time being. So we have a set of worlds, W, and we have a gadget, G, and I'll argue by example later on, G, the gadget, will interpret the modal operators. And I'm not saying anything that is in any way spectacular here. So we interpret propositional connectives as expected. So if you wish, we're taking the Boolean algebra, which is the power set of the worlds, and just interpreting the propositional connectives there. And here, of course, I'm not telling you anything, and I'm not telling you anything interesting in particular. The interpretation of a modality will depend on the gadget. And I want to speak about gadgets. And I want to use them as examples. So, of course, a binary relation on the set of worlds will be a gadget, and we can interpret relational modal logic, the modal logic K and extensions. If we want to reason about possibility, knowledge, etc., etc. So everything that usually finds a semantics in terms of binary relations with certain properties. So if we want to reason about probability, we want something different. So we want something that captures, so mathematically captures the essence of what it means to talk about probabilities. And the essence of talking about probabilities is, of course, a probability distribution. So this means that if we want to talk about probabilities, in order to justify the axioms that we're using, we want to hold this against a semantics that is actually defined in terms of probability distributions. So I want to give you an example. If we have the notion of a truth set, and these are all the worlds in which our formula holds, then we can, of course, define a modal operator, LP, and LP stands for with probability at least P. And these are all the worlds. such that the probability of the truth set of A is at least P. That is, of course, not quite correct because we want something that is local, that is not truth functional. So we want a mu W to be a probability distribution for all W in W, and then we can add the index here. So effectively, we're talking about Markov chains. We could also have a binary operator says that to say that A is more likely than B, and this would be saying that mu W of A is greater than or equal to mu W of B, etc., etc. So if we want to talk about default implications, what people generally use is what's called sphere semantics. So our world is in the center of a set of spheres. So here are all the spheres. And the idea is that the further out you go, the further away are you from the spirit of the world in which we're living. So if something is normally true, it is true in the world that requires the least modification looked at from the center of the spheres, the world where we are now. So different gadget coalitions of agents. So we have what's called a game frame. So there's again a set of worlds at every world. And for every agent, we have a set of strategies. And once every agent has picked their strategy, we will feed this in an outcome function, which is if. And the outcome function will define the next position on the game board of the strategic game. So the worlds, we can think of the worlds as being positions on a game board. So this is kind of the type of semantics that you want, right? Because if you have axioms that are sound and complete, then you really know that you're talking about agents or probabilities or whatnot. Okay, but this, of course, makes life a lot more difficult. So specifically, when you want to look at this from the perspective of trying to have uniform constructions that work for just more than one gadget and for an entire family of logics. And the difficulty is the non-uniformity that comes with the gadget. So a relation is different to a probability distribution, is different to a set of spheres, etc., etc., etc. So and we also cannot really lean on duality. So if we have a Boolean algebra with operators, we can, of course, construct kind of, we can think about writing piggyback on stone duality and construct ultrafilters. But the difficulty is the construction of the gadget. And there's sort of a minor, quote unquote, you can see this as a major, I see it as a minor difficulty that if we do this, we have an infinite model, we get something that looks a bit like a descriptive general frame, but not a frame, which means we have to deal with admissible valuations. So the only thing I want to say here is that it's not easy. And what we want to do, as usual, is we want to align the semantics and the syntax. This is one of the things we want to do. This is where I want to start off with. And because we're not monotonic, we're taking a logic as a set of formulae that contains propositional tautologies, is closed under modus ponens uniform substitution, and not necessitation as you might expect, but congruence instead. So if A and B are equivalent, then box A is equivalent to box B, or box A implies box B. And we have the usual notion of frame validity. So every frame defines a logic. It's easy to see that this is actually a logic, where by frame, I mean a set of worlds together with a gadget in the style that you've seen before. So here are examples. So neighborhood frames are just Boolean algebras with functions in disguise. So the power set as an operation is, of course, self-adjoint, which means that this is equivalent to saying that we have a function on the Boolean algebra, which is the power set of worlds, and we have the algebraic interpretation as just couched in the context of frames. And of course, we can also add axioms such as monotonicity, distributivity, etc., to define a logic. This is all very standard, but we're doing this with gadgets and not necessarily monotone operators. Now, the question is, what, if anything, can we say at this level of generality? And this is where we meet David Lewis again, who in 1974 published an extremely insightful paper, which I think doesn't get the recognition it deserves. And it's about non-iterative logics. And by non-iterative, I mean that the modal rank, so the nesting depth of modal operators, is less than or equal to 1. So if you think in terms of Kripke frames, you have box P implies P is okay. Box P implies box P is not okay because the nesting depth is greater than 1. And what Lewis showed is that whatever set of axioms you take, look at the neighborhood frames, W arrow power set W, and the interpretation of formula A, or of, let's say, box A. This also works for n-array modalities. Let's call this, I don't know, sigma, are the W such that sigma, such that A, the truth set of A, is an element of sigma of W. So this gives us an interpretation of modal operators, and we just take those neighborhood frames for which the given axioms are universally valid. That defines a class of frames. with respect to that class of frames, we automatically have completeness. Full stop. No need for a switch up. But this is, of course, restricted to just one very particular semantics, and these are neighborhood frames. So lots of axioms at the same time, but only one very particular type of semantics. And if we want to take the notion of the idea of gadgets to interpret modal operators more seriously, we need to do something different. And if we are agnostic, at least for the time being, about which gadget. So you imagine you close your eyes and you don't know whether you're talking about probability distributions or non-monotonic conditionals, which is kind of hard to move around in space. So what is the thing that the only thing essentially that you can do is you look at coherence conditions that link the gadget and the axioms. So I don't want to go into these coherence conditions in detail. So one example that I want to give in passing is that if you do this for modal logics that you know and like, for instance, the modal logic K that we all know, this is not the only example. We can do this for coalitions of agents and spheres and probability distributions, etc., etc. For the modal logic K, checking these coherence conditions that imply completeness is a proof that you can do in 3 to 5 lines, depending on how explicit you want to be. And all the rest, the model construction, etc., is all taken care of for you. So when you do this, you get weak completeness. And the constructions are finite model constructions, which means that you kind of get decidability as well, because you can kind of run proof search model constructions in parallel. But that's of course not quite true. For example, if you think about models for probability, so there, essentially, the gadget assigns to every world a distribution on the set of worlds. And of course, if you have 2 worlds, then you can already have an infinite number of distributions. So decidability holds, but it's not quite so easy. And of course, we get finite models because we're kind of vastly more general. The reason we get just weak completeness is because strong completeness, not of course, but fails at this level of generality. So this means we sometimes need to lower our expectations of what we can prove. And an example is, for example, let's say that the probability of A is at least P, where let's say P is less than 1, together with it's false that the probability of A is 1. And this is an infinite set that is clearly not satisfiable, because I have a notion of going to the limit. Okay, now let's move to the proof theory of these things. And I want to talk about two aspects of proof theory. One is sequence calculus, and the other one is resolution. And sequence calculus is something that I've been inspired to look at because a long time ago I did a thesis in Munich, and there are of course lots of proof theorists, and despite the fact that Helmut Schwittenberg was not my supervisor, he had this book with Schulstra, and sort of structural proof theory was a thing. And then for resolution later, I was inspired by the work of Claudia, who's in the audience, who does a lot of modal resolution, and she'll tell us the secrets of her trade a bit later. Okay, now let's talk about sequence calculus. I don't think I need to convince you of the benefits of sequence calculus or why we like sequence calculus. So, even if we have a finite model property, as we've seen, we cannot get decidability. If we have a sequence calculus, we can usually do this if we have the subformula property. We have a new proof principle, induction on proofs, which of course we also have for standard Hilbert type axiomatizations. It's just that modus ponens shoots everything down. And that allows us to prove things like interpolation, but also simple things like consistency. So people that are more closely aligned with philosophy often claim that sequence calculus is nice because it also adds meaning and explanation to not only the modal operators, but I guess to all the logical operators. And so the idea is that each sequence rule kind of deconstructs one connective. I think of sequence calculus from the perspective of automated reasoning, which means I read the rules from bottom to top. So the connective or the main connective will disappear and be deconstructed. Okay, so this is boring. This is the most boring slide. What this slide says is I'm doing what everybody else is doing as well, right? I'm going to look at multisets of formulae. I'm going to write comma for union. I'm going to elide braces when I talk about singletons. I'm going to conceive of sequence as being two-sided. So we have something of the form gamma sequence arrow delta, where gamma and delta are multisets of formulae. And what do I mean when I write this? I mean the conjunction of gamma implies the disjunction of delta, and of course this I can embed single formulae, or I can represent single formulae as sequence as well. Okay, now that's the boring stuff. This is also kind of still quite boring, but at least we see a couple of things happening. So we have fixed our propositional syntax, and I hope that we have fixed it to include conjunction, negation, propositions, and falsity. If not, this is what we should have fixed. And there is a rule for each connective. So these rules are very standard, and they are indeed the system called G3P from the book by Schulstra and Schwittenberg that I've mentioned earlier. And we have a standard notion of propositional derivability. So the sequent gamma gives delta can be derived Now there's only one thing that's slightly non-standard here. From a set capital Phi of given sequence that we consider to be additional axioms. So usually in many expositions, this set will be empty, and sequence calculi with additional axioms are not a simple beast to deal with, because sometimes or quite often lots of properties break. So we're going to use this very carefully, but I want to include it just for the sake of mentioning it, or for the sake of having the option to use it later. And then what we want to look at is structural proof theory, and we want to piggyback on propositional logic, right? So here's the extent to which we can piggyback on propositional logic. And these are things that I just want to mention. So here we have an example of an inversion rule. So if I have proved a sequence with a negated formula on the right, then the question that you ask yourself is, okay, how did this happen? And of course, one answer is that from gamma A, we have proved delta somehow, and then applied negation introduction on the right. But of course, that's not the only way in which this could have happened. And what the inversion lemma tells us is that, okay, we can actually assume that this was our premise. So this holds for propositional rules. Then we have other things that we can add without increasing the set of provable sequence. This is weakening. We can always add more assumptions. So because we're fully structural, the multiplicity of a formula in a sequence doesn't matter. And at this point, you might ask the question, if we have this rule, why the hell have we started out with multi-sets? And I'm not going to answer this question, but maybe I'll say more about it later. That's for you to ponder for the time being. And here is, I guess, the most prominent sequence calculus rule, which is, the cut rule, which essentially takes the rule, plays the role of modus ponens. In particular, what is happening is that there is a formula A in the premise which doesn't appear in the conclusion. So if you want to hold this against modus ponens, we have A implies B and A proves B. And also, again, you have a formula A that appears in the premise but not in the conclusion, which destroys backwards proof search. On the other hand, it's very useful to have the cut rule to make the connection to logics that are given just by stating a bunch of axioms. Okay, now let us try and prove, and I'm using a rule, a logic that you know, which is the modal logic K. Let's try and prove that a a sequence calculus for the modal logic K is sound and complete. But let's do this with having the idea of generalizing this to other logics at the back of our mind. Okay, so here's the rule set. This is on the right. These are the axioms. Necessitation, which we can replace by congruence if we have box top, and the model distribution axiom. And we want to prove soundness, which means that if a formula is derivable, then it is actually an element of the modal logic K, which means the least set that contains propositional tautologies, the distribution axiom, is closed under substitution, yada, yada, yada. And that is easy because we just need to show that the set of formulae that is derivable in the sequence system has these closure properties. And that is an easy proof. Now, let's try and do it the other way around. And let's do this in 2 steps. So, if A is axiomatically derivable, then A is derivable in the sequence calculus. And this is also easy if we allow ourselves to use the rule of cut. So essentially what we can do is we can simulate every proof in the axiomatic system by means of sequence calculus rules. And when we appeal to closure under modus ponens, we use the cut rule. So, but that's not quite enough because in order to have these wonderful properties of backward proof search, etc., we want completeness without the cut in this sense. So the thing that becomes important now is cut elimination. And this is really at the heart of the matter. This is what I wanted to get to in a sort of admittedly maybe slightly long-winded approach. And the observation is that if we have a cut on modal rules, so here on box A0, so this is how it looks. This is the cut rule, of course, and we have premises. And what you see is that we also have an occurrence of A0. And this looks like we can apply cut backwards. And we have A1, AN, B1, BK gives B0. And to that sequent, we can, of course, apply the K rule to get this conclusion. So this means that cuts between modal conclusions can be replaced in this particular example by possibly different instances. So the instance on the left has NAs, the instance on the right has KBs, the instance that I'm replacing with has N plus K formulae on the left of the modal sequence arrow. Okay, so if we can do this, we see that we have consistency because the empty sequence, for example, is not derivable. We have under mild conditions polynomial space complexity by using that p space is the same as alternating polynomial time. If the modal rules kind of look similar to the ones that we had for K, and this is one thing I want to talk a bit more about. So I'm going to split more applications to interpolation and rather talk about proof rules. So what we had is, I've given you one example, and this is a boring example because it's well known and well studied in the literature. And there was a proof rule that just fell from the sky, right? I told you, this is it, and we could use this and have cut elimination, and then we get all these amazing benefits. But where does it come from? Right? So I want to look at the sky, and I want to see how this rule actually came about. And again, this is a process that we can do with any axiomatization of a modal logic to turn it into something that gives us sequence calculus where we get essentially cut elimination for free. So let's start with this rule and this axiom. And let's try and coach this in sequence calculus form. So on the left, this is necessitation. On the right, I apply inversion to get an axiom that looks like this. And I can see people nodding, which tells me that I don't need to speak more about it. And now I'll look at possible instances of cut. Okay, so that means I need to instantiate these two rules. And I'm going to instantiate the rule on the left with A implies B. And I'm going to instantiate the rule on the right with identity. And then I have a cut on box A implies B. And I get box A gives box B. And the premise, if I apply inversion, is A gives B, which means I've just found myself a new rule. So let's add this rule, and because we liked it so much, let's just do it again. Okay, now we have three rules. This is our newcomer. And now I'm going to instantiate the B here with a B arrow C. And I'm going to do the same for the distribution axiom. And then I'm going to have a cut. And I'm going to apply inversion here. And then I have a second rule. And I just keep going until I found no more rules. And this gives all rules of this form. And we just keep adding cuts between conclusions until the process saturates itself. And this gives terms and conditions apply a set of rules which we derive purely syntactically, and we've done this for graded agent logics, probabilistic modal logics, etc., which is cut-free. Okay, so the terms and conditions that apply are that we need to make sure that contraction, inversion, and weakening are being kind of built into the rules, are being absorbed. And this is also a difference to the rule that I showed you initially. The rule I showed you initially had a weakening context here, gamma and a delta, right? So this is what we still need to take care of. So admissibility of weakening, we get this by adding weakening contexts. And we can show that if we have any two instances of this rule and a cut between them, this is something that we can actually get rid of by using a new instance. Okay, so for all the others, we might need to do a bit more work. So this is, again, a simple example, but an example where this works. So we now have a new axiom, namely the T axiom. And again, we do the same thing and we look for cuts. And then we get this rule. But this rule is not closed under weakening and inversion. So we need to modify it. And of course, keep track of the fact that all the modifications we do are actually sound. And here it becomes more interesting. Application admissibility of contraction. So what happens if we want to contract box A here with another box A, which is in gamma? So this is something that we cannot push into the premise. On the other hand, if we have box A in the premise, then of course we can push contraction up the proof tree, and this gives rise to conditions that you can check locally. So cut between modal rules can be replaced by other instances. You have admissibility of contraction and weakening and inversion, and then you automatically have a cut-free proof system. Okay, so now I want to do yet another pivot and tell you about, so this is the most recent work. This is joined with Claudia, as I've mentioned earlier. She's inspired the work on modal resolution. So why should we be interested in resolution? One of the reasons is that it just works amazingly well in practice. And resolution is very different from the sequence calculus. Actually, this is not true. This is the premise that I want to start off with now. And then in 9 minutes, I hope that I've convinced you of the opposite. Okay, but let's stick to the premise. So this is the resolution rule of propositional logic that I think we've all learned about in Logic 101. And this is very clearly very similar to the cut rule. So in sequence calculi, we're typically after cut-free because that helps us to do backward proof search, etc. So sequence calculi operates on formulae or on sequence. Resolution operates on clauses. So the point of difference is that a clause doesn't have any nesting of operators, whereas formulae can be, I don't know, a conjunction of a disjunction of a box of another box, etc., etc. They can be deep. In resolution, we're dealing with clauses that are shallow. And in the sequence calculus, we have lots of rules. I've shown you an axiomatization of propositional logic. In resolution, there's just one, namely the cut rule. So, but in order to actually convert a deep syntax tree that represents a formula to something shallow, sequence resolution needs pre-processing. So this is essentially to make things shallow, Whereas with the sequence calculus, we just start with a formula and then we deconstruct it and Bob's your uncle. So right now I claim that they're very different. So let's have a slightly more closer look at what happens under the bonnet. So how do we make things shallow? Well, we use variables to represent formulae, and we add the definitions of these formulae. So if we start with A and B, we want to make this shallow. We want to flatten this into a clause. We introduce a new variable, R sub A and B, and we add clauses that define the meaning of this variable. And these clauses are essentially RA and B is equivalent to RA and RB. And we can express this in clause form, as I've done. And if we take these clauses, this is what you can see on the right, we can actually read them as sequence, right? So the clause on the right is just RA and RB implies RC, which we just put a sequence arrow between the negative and the positive variables, and we have the same meaning. And if we do this, we can take a sequence rule like this one, conjunction intro on the right, and we can transform it into a resolution derivation. So where do we apply cut? So here we have RA, here we have not RA, and then here we have not RB, and here we have RB. So this means that, so the same works for all the other propositional rules. This means that we can simulate all the sequence calculus derivations. So, but there's one strange thing that's happening, namely, when you learn or read about resolution, you learn that resolution is a vehicle to prove that something is inconsistent. If you want to prove that B is a consequence of, I don't know, a bunch of axioms, you say, okay, I'm going to take the axiom, I'm going to negate the formula B, and then I derive a contradiction. This is how resolution works. But with what I've just shown you, it seems that actually, if I can prove something in the sequence calculus, I can also prove it in the resolution calculus because I can simulate all the rules. So that means in order to prove inconsistency of A, what we can do is essentially add a formula that says A is actually true and translate the negation. And the other difference is that here we're going to consider sets rather than multisets of formulae or variables. And one interesting question on that is what happened to the cut rule, right? So at no point in the sequence calculus did we kind of use the cut rule, but we have it available in resolution. So if it's kind of there, why don't we use it in the sequence calculus? And the answer is the causal translation. So the causal translation takes a formula and produces a bunch of clauses, but it only produces variables for subformulae, which means that if we have something that would generate a completely new formula, in the causal translation, we wouldn't be able to speak about it, which means that in order to translate the sequence calculus into a resolution calculus, we seemingly paradoxically need that the sequence calculus be cut-free. Despite the fact that in resolution, the only thing that we care about is the cut rule. So here is the translation formally. So now we add modal operators, and essentially the translation says that hearts of R A is equivalent to R of hearts A. So that's easy. And now we add modal rules, right? And the modal rules are those that come from the sequence calculus. So there's a sequence calculus rule on the left, and there's a resolution rule, resolution in quotes, right, on the right. So it's in quotes because it's not actually in the spirit of resolution. And so our sequence calculus rules are formulated in terms of variables, and the instances in the sequence calculus allow us to sub in a formula for a variable. So here we are just allowed to sub in another variable. But this means we can formulate the conclusion perfectly. And for the premises, we do the same, but we just require that we have subclauses of the premises of the sequence calculus. And this is because propositional resolution is not complete, it's just consequence complete, which means that the only thing that we can hope for is the same when we add modal rules, which means that we cannot expect resolution to prove the premise exactly, but a subclause is good enough. And this gives a first translation theorem. And if we have cut, congruence, and weakening be admissible, this allows us to take cut-free sequence calculus and convert it into a resolution calculus, and both of them prove the same formulae. Okay, and
2 more minutes.
Two more minutes. Yep. Okay, so we can do this with a lot of logical systems, right? This is going back to the initial program. So these are a bunch of conditional logics with modus ponens. This is the rule for conditional modus ponens. This is the rule for the multi-agent logic, and it all works. So we just do it once and for all. And I'll take 1 minute to give you an idea of something different that we can do to make the development more in line, to make the resolution calculi look more like resolution, actually. And the idea is that we take, for example, this rule, which is the congruence rule, and we say that when R box P and not box Q inconsistent. So, of course, when P is equal to Q, but it actually suffices that P is equivalent to Q, right? Because we have congruence. And S1 and S2 essentially together express that P and Q are equivalent. So if P and Q are equivalent, then box P and not box Q are inconsistent. So if you look on the left, L and not L are inconsistent without any further assumptions. For box P and not box Q to be inconsistent, we need these two assumptions S1 and S2. But essentially, we can copy the rule on the right, which is just propositional resolution, and make it into a modal resolution that says we can perform a cut if these two atoms that are boxed in blue are inconsistent. So this gives us a way, this also is a way that works in general that allows us to construct calculi that are more in the spirit of resolution from a cut-free sequence calculus. This also works a lot more general. And I want to close here and say that what I've tried to convince you is that we can do lots of things by sort of taking a step back without having to look at the concrete details of a given logical system and try and aim for results that are more general. Multiple proof systems are a useful thing. And you've seen 3 different ones with all with their different benefits. And we want to do more of this work specifically to transfer results between sequence calculi and resolution when it comes to complexity and efficiency. Thanks very much for your attention. That's all I have for today.
We can have questions. Okay, time for one question.
Okay. Could you tell me a little bit about like the technology of the evolution, the relationship to the non-monotonicity, which is part of the title of the talk, because I don't see the connection yet. But is there like maybe like a resolution is kind of like a better way to deal with the non-monotonicity or anything rather than sequence calculus? Yeah, I just very curious.
So I'm not sure whether the answer is going to be satisfactory, but at no point in the development of all this are we assuming monotonicity.
Okay.
And what I should have said is for not necessarily monotonic or not necessarily normal logics, and this is usually abbreviated by saying, okay, I'll talk about non-monotonic things. What I really mean are not necessarily monotonic. So that is essentially to highlight the generality.
Thanks. Well, I mean, I have a quick question. So for the so you gave some complexity for the validity problem. What about entailment? A theory entailing phi, formula 5. Do you know what the complexity? Like, there is a paper for modal logic, right? And complexity of entailment. There is only one paper, as far as I know. But if, for example, this is not in the handbook of modal logic, in the chapter of complexity, there is almost no information about entailment. I'm curious. Have you looked into this?
No, I haven't, and certainly not at a very from a very general perspective.
Right. Okay. Thank you so much. Okay, guys. So let's thank everyone.